Hi. Now in today's video lecture we will go through overlapping of orbitals, right? So now we are already clear with the concept of orbitals, right, as we have done in the previous chapter, structure of atom, right? So here we would be looking into overlapping of orbital from the perspective of bond formation. We will see how overlapping of orbital will result into bond formation, right? So one thing we know that the covalent bond is formed by sharing of electrons, right? It is formed by sharing of outer electrons, the valence electrons of the atoms, right? So we know from structure of atom that the shells, right, these shells consist of subshells, right, and subshells are based on the orientations, they form different orbitals, right? Subshells consist of different orbitals and it is these orbitals that contain electrons, right? So the orbitals of valence shell, right, actually it is these orbitals that participate in bond formation. If you look into more deeper into chemical bonding, into covalent bonding, you will see that it is actually not outermost shells that take part in bonding, but it is the orbitals, right, of valence shell that take part in bonding, right? And we know that an orbital can contain maximum of 2 electrons, right, as per Pauli's exclusion principle, right? So when two atoms approach, right, to form a chemical bond, for example, if two hydrogen atoms approach to form a chemical bond, we know that its outermost shell contains 1 electron, right? And that 1 electron, if you look at the electronic configuration, is contained in 1s orbital, right? So when two hydrogen atoms are approaching, their orbitals, these orbitals are not fixed path but they are waves, right? These are electron waves, right? So when two atoms approach, right, their electron waves will interfere with one another, right? So when these electron waves will interfere with one another, they will overlap, right? These waves or these orbitals are nothing but electron clouds, right? So we can say that when two atoms approach one another, their electron clouds will overlap with one another, right, or interfere with one another, resulting into the formation of covalent bond, right? So now let's talk more about it. We know that if this is your x-axis, this is your y-axis, this is your z-axis, right, and this is your s orbital, right? Similarly, and this is an s orbital which is an electron cloud, right? If you remember, this was constructed using the value of psi, right, using the various values of psi square at different points, right? And psi is a wave function that contains all information about regarding this electron, right? So this electron cloud was constructed using psi square, the value of psi square at different points that represents the electron density. So this orbital is nothing but, it is a region where the probability of finding that electron, in case of hydrogen the valence electron, is maximum, right? So in covalent bond formation, it is the sharing of electron that takes place, and these electrons are contained in these orbitals, right? So when a bond formed between two atoms, it is actually these orbitals that will interact with one another to form a bond, right? Now we have to see what the kind of interactions that will result into bond formation and the kind of interactions that will not result into bond formation, right? And there is p orbitals, if you remember, this is how it will go, right? This, right, then you have this z axis, this is your px orbital, this is your py orbital, and this is your pz orbital, right? So these are different orientations of p orbitals, right? P orbitals have three orientations: px orbital, py orbital, and pz orbital, right? And this is your s orbital. S orbital have only one orientation, right? Similarly, you have d orbitals. We have learned about d orbitals also. You can just look at my previous video lecture, right, on these orbitals if you are not clear on the orbital concept, right? But just remember one thing to know this, that the electrons that we talk about that are revolving in any of the shells, right, is actually contained in orbitals, right? And an orbital can have maximum of 2 electrons, right? So electrons are present in orbitals, right? This is first point. Second important point is these orbitals have different orientations in space. They have different orientations in space, right? Electrons are present in orbitals and they have different orientations like x, y, z, px, py, pz axis, right? And when a covalent bond formation takes place, for example, 1s orbital, it contains 1 electron, right? So actually when a hydrogen molecule forms, right, it is actually these 1s orbitals of outermost shell of hydrogen atom. It has only one shell, right, that interact, right, and it is actually their electron, it is actually the orbitals are electron clouds, right? So it is these orbitals that are approaching one another to form a bond, right? And their electron clouds will overlap with one another, right? And this is the common electron cloud, right? This is the electron cloud that now belongs to both the electron clouds, or this overlapping region of orbital belongs to both the orbitals. I'm sorry, it belongs to atoms of both the orbitals, right? So this is your overlapping region, right? Overlapping region of the orbitals, and this belongs to both the orbital, right? Now the electrons, if you remember, when hydrogen molecule forms, the 1s orbital, if this is your one hydrogen atom, this is your second hydrogen atom. So both these hydrogen atom, what they will do is they will share their 1 electron, right, which are actually present in this 1s orbital, right? And this 1s orbital is an electron cloud. So the common region, right, of this overlapping common region contains these 2 electrons, right, which results into bond formation, right? We know that a bond formation is nothing but when these electrons are shared, right, between 2 atoms, a bond is formed, right? So this is how these electrons are shared. The shared electrons are present in this common overlapping region, or this shared overlapping region, right? And we call it as bond pair of electrons. So bond pair of electrons that result in covalent bond formation are actually present in this overlapping region, or the common shared region that now belongs to both the electron clouds, right? So this is the basic concept, right? And since in this concept, right, the valence bond theory is based on this overlapping concept of orbitals. This concept, the concept of orbitals, is taken from wave mechanical model of atom. So since we say that valence bond theory is based on the overlapping of orbitals, so in a way the valence bond theory is based on the wave mechanical model of atom, right? So I'll just mention it over here, VBT, valence bond theory, and also molecular orbital theory that we will do in future. in different video lecture, VBT is based on overlapping of orbitals, right? An orbital concept is taken from wave or quantum mechanical model of atom, right? So what we say is that VBT is based on wave mechanical model of atom, wave or quantum mechanical model of atom. Right? So from here we know that a bond formation takes place due to overlapping of orbitals, right? So the most important point is that bond formation takes place due to overlapping of orbitals, right? Now we will look into orbit overlapping that will result into bond formation and overlappings that will not result into bond formation, right? Because we also said here that these orbitals have different orientations in space. If you look in x-axis, y-axis and z-axis, all these orbitals have different orientations except for s orbital, right? It has only one orientation. If you look at this p orbitals, it has 3 orientations. If you look at d orbitals, it has 5 orientations. If you look at f orbitals, it has 7 orientations, right? So depending on the orientations of orbitals, right, of atoms that are approaching to form a covalent bond, a bond formation may take place, a bond formation may not take place, right? So let's see what orientations, or let's talk about orientations only right now. So let's look what orientations will result into bond formation, right? What is the favorable orientations that will result into bond formation, right? So orientations of orbitals while bond formation. Right? So these orbitals, right, of any atom, right, the orbitals of any atom, say hydrogen fluoride molecule is forming, right? When hydrogen fluoride molecule forms, right, suppose this is your hydrogen, this is your fluorine, right, it will form hydrogen fluoride molecule, right? This is a covalent molecule. So if you look based on this concept, the formation of hydrogen fluoride molecule, hydrogen has only one electron, it has one orbital, one electron. And if you look at the electronic configuration of fluorine, it's 1s2, 2s2, 2px2, it's 1s2, 2s2, 2px2, right, 2py2, 2pz1, right? This is the electronic configuration of fluorine, and we said in the previous video lecture that in order to understand the valence bond theory, you need to be good with the electronic configuration, right? If you know how to write electronic configuration, then only you would be able to find out which of the orbitals would be overlapping, right? Kind of. And one important thing is the bond formation will result only when half-filled orbitals interact, right? Bond formation takes place due to overlapping of half-filled orbitals only, because we know that as per Pauli's exclusion principle, an orbital can contain maximum of 2 electrons, right? So when this kind of bond or this kind of bond is forming, right, the overlapping, the orbital, right, the orbital that are interacting, right, they are half-filled orbitals, right? So bond formation takes place due to overlapping of half-filled orbitals. Half-filled orbitals. We know that an orbital contains 2 electrons, so half-filled means the orbital that contains 1 electron, right? Whether it is s orbital, p orbital, right? It should be half-filled. So if you look at this example from this half-filled orbital concept, this orbital contains 1 electron, this is half-filled, this is half-filled, so both these interact to form this, we call it as molecular orbital. If we will do this in molecular orbital theory, it forms a molecular orbital that has 2 electrons, right? Similarly, if you look at hydrogen fluoride molecule, it has 1s orbital, right, and it has half-filled 2pz orbital, right? Now these two orbitals will interact, 1s and 2pz orbital will interact, right, to form a bond between hydrogen and fluorine, right? So what we say is 1s orbital of hydrogen atom will interact with 2pz1 orbital of 2pz orbital of fluorine atom, right, to form hydrogen fluoride molecule, right? So how it looks like actually in space, if you look at it, it would be like this. Right, this is the 2pz orbital, sorry, this is the 2pz orbital, right? So this is your s orbital, right? So s orbital will interact this way, right? So this is the overlapping region, right? This is the overlapping region, and both these orbitals will contain both these orbitals are half filled, that is they contain 1 electron and should be in opposite spin, right? Because this is what Pauli's exclusion principle tells us, that the 2 electrons in the orbital should have opposite spins, right? So both these approaching orbitals will have electrons in opposite spin like this. That is why we draw electrons, these arrows showing that electrons have opposite spins, right? So this region will contain electrons from both these half-filled orbitals in opposite spins, right? So orientation of orbitals is important, right? And when these orbitals are overlapping, right, we know that these orbitals are nothing but electron waves, right? So, and waves have amplitude, right? We know this from properties of waves, that waves have amplitude, right? So we look at we will look at this overlapping concept from wave concept of electron, right? That these electrons are waves, right? They have wave character. So these orbitals are electron waves, right? And waves have amplitude. If suppose this is the wave, right, this is the wave, right, and this is its amplitude, or this is its amplitude, right? If you look, if this is the x-axis, then this is in positive, right, upper x-axis, this is in negative x-axis, right? So when overlapping takes place, right, the orientation of orbitals should be same, right? When we say orientation of orbital should be same, is that px orbital will overlap only with px orbital of another atom, and py orbital of one atom will overlap with py orbital of another atom, right? This is what it means, right? So we'll write it over here, that overlapping orbitals should have same orientation, in space, right? They should have same orientation in space. Example, py orbital will overlap with py, px orbital will overlap with px, right, and pz will overlap with pz, and any of these can overlap with s orbital, right, because s orbital, its orientation is same in all directions, right? So this is how what it tells us, right? So just understand this so that it is easy to understand your future lectures that that we will be doing hybridization, right, and molecular orbital theory in detail, right? So this concept should be clear, the overlapping of orbitals, right? So now let's look into little more into it. So the orbitals, the orientation of orbitals should be same, right? So we say that their overlap may be positive, negative or 0, right? Their orbital overlap, say that the overlap may be positive, negative or 0. What do we mean by this? Positive overlap is this, right? When positive side, right, this side will overlap with this side only. That means when two waves, these are two waves, right, or these are two waves, when these waves like overlap, they form a bigger wave of bigger amplitude, right? This is what it actually means, because we said that these are nothing but electron waves of this type, right? So when these two waves overlap, right, it is somewhat like this or it is somewhat like this, they will form a bigger wave, right, of bigger amplitude. So positive overlap means that orbitals that are in same phase, right, they are interacting. That is positive lobe, right? This, if you look at this, this is the positive lobe, this is the negative lobe, this is the positive lobe, this is the negative lobe, right? So positive lobe will interact with positive lobe of another hydrogen atom. So negative lobe will interact with negative lobe of another hydrogen atom or another atom, right? So this is the kind of overlapping, right? So positive is overlapping with positive. Let's draw it like this. This positive lobe overlaps with positive positive, right? And another kind of overlapping is like this. This is your PP overlapping, right? And this is your s orbital and this is your p orbital. So this is your sp overlapping, right? Similarly, if I take this, suppose we take two py orbitals, right? This is again positive overlapping. Sorry, the positive lobe, this is the positive lobe and this is the negative lobe. Right? So negative lobe overlaps with negative lobe, positive lobe will overlap with positive lobe, right? And what kind of negative lobe overlapping is? Negative overlapping is like this. If the positive overlap, the positive lobe of one p orbital overlaps with negative orbital of negative lobe of another p orbital, right? So this will not result into bond formation. This will result into bond formation, right? Or if you look at this type of overlapping here, this was positive, right? If negative region or negative lobe of this orbital interact with positive region or positive lobe or positive p orbital, s orbital, this will again not result into bond formation, right? Or if the overlapping is like this, positive negative, then this will again not result into bond formation, right? Or there is something known as zero overlap, right? So what do we mean by zero overlap? By zero overlap we mean like py orbital, if py and px orbital will try to overlap, they would be zero overlapping, there would be no overlapping, right? So like this, if this is your px orbital, right, suppose this is your py orbital, right? So this is your zero overlapping, this is your zero overlapping, that is no overlapping, no bond formation, right? Similarly, this is also, if you look at this kind of overlapping is also your zero overlapping, right? This s orbital is trying to overlap with this p orbital, right, in this orientation. This is your zero overlapping, right? So overlapping should be, you should be clear that the overlapping orbital should be similarly oriented, they should have same orientation in space, and only when orbitals have same orientation in space they will result into bond formation, right? And their negative lobe should overlap with negative lobe, and positive should overlap with positive lobe, so that a bond formation takes place, right? And the strength of bond, we say the bond formation takes place, right? It is actually this bond that is getting formed here. In case of hydrogen fluoride molecule, this bond is getting formed now. Here also, if you will see, these are orbitals, right, that are overlapping. This is the overlapping region, right, that now belongs to both the orbitals, right? And this is your nucleus, positive nucleus, and here in the overlapping region you have these two electrons, right, that are actually forming a bond, right? And these electrons are equally attracted by both the nucleus, right? And it is these electrons that hold these two atoms together, right, in a molecule, right? So this concept should be clear, that this overlapping region contains these bonding electrons, right? And these bonding electrons can be exchanged, it can go into this region, and this can go into this region, right? They can exchange spaces, they can exchange their place. So, and the strength of the bond, right, actually depends on this overlapping region, right? Better is overlapping, stronger is your bond, right? So this is important, that strength of bond depends on the overlapping of orbitals, right? More is overlapping, more is your bond, more strong is your bond, right? So write it over here, that strength of bond depends on overlapping, right? Strength of bond depends on the overlapping of orbitals. And this type of overlapping, when you will see, right, pp overlapping, right, or this sp overlapping, right, these are head-on overlapping, right? This is your head-on overlapping. This kind of overlapping is your head-on overlapping. Head-on, or we also call it as end-to-end overlapping, right? And this will result into a stronger bond, right? And this type of overlapping, where you see this similarly oriented px or py orbitals overlapping, this is your sideways or lateral overlapping. Sideways or lateral overlapping, right? This is better overlapping. Overlapping is more in case of head-on or end-to-end overlap, and overlapping is less in case of these sideways or lateral overlapping, right? So this is your weak bond. This will result into weak bond, which we call as pi bond, right? And this will result into a strong bond, right, which we call it as sigma bond. We will do sigma and pi bond in detail in next lecture, right? So remember this, right? So I hope all this is clear. Just remember the concept, remember that all these points, right, of overlapping points, and how overlapping will result into